This episode introduces the Ice Age cycle found in Antarctic ice. Antarctica is the largest continental glacier on Earth, which needs no further explanation. More than 99% of Antarctica, excluding some coastal areas, McMurdo dry valleys, and the mountainous regions, is covered in a vast mass of ice called the Antarctic ice sheet. Antarctica covers an area of 14 million square kilometers. Its area is 1.44 times larger than the United States, almost twice Australia's size. The Antarctic ice sheet is more than a kilometer thicker than the Greenland ice sheet and is nearly 4 kilometers deep at its thickest point. Bordered by the Transantarctic Mountains, to the right is East Antarctica, and to the outside is West Antarctica. Both the east and west sides are covered by a vast ice sheet, and to the north and south of these mountains are adjacent ice shelves, glaciers floating on the sea. To the north is the Ronne Ice Shelf, and to the south is the Ross Ice Shelf. The Antarctic Peninsula is adjacent to the Ronne Ice Shelf. The McMurdo Dry Valleys, an area of extremely low humidity and no snow or ice in Antarctica, are located in Victoria Land, west of McMurdo Bay and the Antarctic Ross Sea. McMurdo Station, the U.S. Antarctic Research Base, is located here. The station is the largest Antarctic research station and has over 100 buildings. About 1,000 people stay in summer and about 200 stay in winter. The map shows the boundaries between the sea, where dashed lines indicate the ice shelf floats and the continents. So, since when did ice form in Antarctica? It has to go back a very, very long time. There are arguments that the snowball Earth hypothesis in the Ediacaran 600 to 800 million years ago, before the Paleozoic era. However, from the Paleozoic, the Earth's temperature has been confirmed through analysis of seafloor sediments. 4 times since the Paleozoic, Antarctica has been covered with ice. The first is between the Ordovician and Silurian about 450 million years ago. And as you can see on the graph, Earth's temperature dropped abruptly at the Devonian Carboniferous boundary. This was the time when the second glacier formed in Antarctica. When Laurasia and Gondwana merged, the Southern Hemisphere supercontinent was formed. I'll introduce the reason for the drop in global temperature at this time through another video. Let's look at a summary graph of the Cenozoic planet Earth. During the Oligocene, or 34 million years ago, Antarctica was covered in ice for the third time. This is related to the opening of the Strait of Tasman. The Tasman Strait is the sea between Australia and New Zealand. The Drake Passage was also opened by the Oligocene, allowing Antarctic glaciers to be maintained. The Drake Passage lies between South America's Cape Horn and the Antarctic Peninsula. The Tasman Sea and the Drake Passage are related to the global thermohaline circulation. This circulation influences the formation of glaciers and interglacials. I'll introduce the concept of this through another video. At the late Oligocene, atmospheric carbon dioxide increases, and the Earth warms again. At this time, the Antarctic glaciers retreat a little. Scientists attribute this to changes in atmospheric carbon dioxide, as well as changes in the oceanic circulation. In the Middle Miocene, atmospheric carbon dioxide drops from 300 ppm to 140 ppm, reducing the greenhouse effect caused by carbon dioxide and lowering the global temperature. An additional proposed Middle Miocene disruption reason is the change in eccentricity in the solar insolation cycle. This climate cooling results in East Antarctic ice sheets growth. Although retreating in the Miocene, Antarctic ice still existed for 3,400 years. Glaciers began to form 2.75 million years ago in the Northern Hemisphere and peaked about 2.58 million years ago. The period from when the Northern Hemisphere glaciers began to grow is called Quaternary glaciation. This coincides with the emergence of Homo habilis. Now is the Holocene interglacial during the Quaternary glaciation of the Cenozoic era. The secret that scientists have been able to figure out the climate for 500 million years and draw the graph you see on the screen is in the oxygen isotope ratio of the calcium carbonate shell, made by foraminifera among the seafloor sediments. The Italian-American scientist Cesare Emiliani largely contributed to the analysis. Please look at the video he and the other scientists linked to in their efforts to find the paleothermometer. Also, Danish paleoclimatologist Will Dansgaard contributed to the age of ice from the Greenland ice cores at about 140,000 years. I also introduce his efforts through the linked video. Ice core studies of the Greenland ice sheet beginning in the early 1960s proved that continental glaciers are sound recorders of climate history. The paleoclimatologists' gaze naturally turned to Antarctica. Paleoclimatologists with adventurous temperaments headed to the land of extremes as if competing to blossom the history of climate engraved on the Antarctic ice sheet. In Antarctica, the Baird Station in the United States began excavating ice cores to the bottom of the continental glacier for the first time in 1967. The screens are stations for studying Antarctic ice. Beginning with Baird Station, excavation work to obtain Antarctic ice cores began in Vostok of the Soviet Union, Dom C and Dom F. Antarctica is known as a common property of humanity, not a territory of any country, as there is no single immigrant there. However, glacier excavation in Antarctica was carried out in an invisible conflict over an enormous amount of oil or mineral resources, including East-West Civil War issues, which are believed to be dormant in the ground. Another ice core has significantly impacted climate change research, such as the one excavated at Camp Century or Summit in Greenland, a series of ice cores excavated at the Vostok Station on the eastern ice sheet of Antarctica. The Vostok Station is a Russia-based location in the deepest part of Antarctica, named after the Vostok, the world's first human-crewed spaceflight, which the Soviet Union, now Russia, is proud of. It was erected in December 1957 at an altitude of 3,488 meters, almost in the middle of the eastern ice sheet of Antarctica. The annual average temperature is -55 degrees Celsius, and the lowest temperature was observed on July 21, 1983, -89.2 degrees Celsius, making it indeed an extreme land. It was in 1970 that a continental glacier core was first excavated at the end of the Earth. Inspired by Camp Century's Dansgaard research, Soviet paleoclimatic researchers collected an ice core measuring 950 meters in length. Oxygen isotope ratios in the core indicated that at only 400 meters, there is an ice layer presumably from the last ice age. Feeling optimistic, Soviet researchers started a project in 1980 to drill longer cores. And in October 1984, they extracted a historical ice core called Vostok 3G at a depth of 2,202 meters. The most significant climate difference between Antarctica and Greenland is that Antarctica receives much less precipitation than Greenland. Annual precipitation in Antarctica averages 100 millimeters, 30 centimeters per year in terms of snow cover, but in some places it is less than 20 millimeters. Considering New York gets about 1,183 millimeters of rain annually, you can see how little precipitation there is in Antarctica. Polar regions like deserts widely distributed in the subtropical areas have excellent downdrafts, so precipitation is low and dry. Ice cores excavated in Antarctica are difficult to recognize because of the thin, soft layer and the amount of snow cover. On the other hand, even with a short core, a long record can be obtained. In Greenland, for example, there are more than 3 kilometers of the continental glacier can be harvested and only date back around 130,000 years. However, an Antarctic core of the same length can be dated back more than 500,000 years, and in some places up to 1 million years. In other words, Antarctic ice cores record a more extended climatic history. Ice is an atmospheric fossil. Research results using the Vostok 3G core shocked paleoclimatic researchers and researchers who predicted future climate change. Chief among them was the reconstruction of atmospheric carbon dioxide concentrations over the past 160,000 years. Immediately after the snow has accumulated, it is fluffy. As the snow piles up, the increasing weight gradually hardens the underlying snow. First, it becomes snow in a granular state that is neither snow or ice. And as time goes on, it becomes more complex with the weight that comes under pressure, forming small holes in the ice. Ice in this state is called firn. Firn weighs about 0.5 grams per cubic centimeter. Since ice weighs approximately 0.9 grams per cubic centimeter, firn is half ice and half air. It becomes ice at the end of it and is further pressured and hardened. In Antarctica or Greenland, the snow that accumulates above is soft and light, and it takes decades and sometimes thousands of years to freeze. Let's take a look at the ice made in the refrigerator. Most of them are white and hazy. This is because when water freezes and turns to ice, the air dissolved in the water cannot escape and is trapped in air bubbles. Once the air in the bubbles is trapped in the ice, it cannot run unless the ice melts or breaks. Something similar happens to the continental glaciers of Greenland and Antarctica. The snow becomes firn, and the air that filled the space between the crystals was trapped in the process of hardening and turning into ice. Ice cores from Greenland and Antarctica are also slightly opaque rather than transparent. What if that ice could be preserved without melting for thousands of years? Of course, the composition of the air inside the bubble matches the atmospheric chemical composition at the time the bubble is trapped. In other words, the air in the ice can be said to be a fossil of the atmosphere, and it is an excellent research material for paleoclimatologists. Analyzing atmospheric fossils makes it possible to reconstruct the atmospheric chemical composition long ago. Hans Oscher's team from the University of Bern, Switzerland, precisely measured the carbon dioxide concentration in air bubbles in ice cores. By analyzing 3 ice cores from Camp Century in Greenland and Bird Station and Dom in Antarctica, they found that atmospheric carbon dioxide concentrations during the last ice age were 200 ppm. The ice core analysis results in Vostok also shows almost the same values, supporting the Oscher's team analysis results. The concentration of CO2 in the atmosphere during the interglacial period before the impact of human activity was about 280 ppm, indicating a 30% lower CO2 concentration during the last age. What is particularly interesting about the carbon dioxide record from the Vostok ice core is that the time-varying pattern is sawtooth, closely resembling the ice's oxygen isotope ratio or Antarctic temperature change. Suppose there's no explanation on the vertical axis of the carbon dioxide concentration in the graph on the screen. In that case, it can be mistaken for ice's oxygen or hydrogen isotope ratio. In addition, looking at the graph, it can be seen that the glacial period and the interglacial period were repeated every 100,000 years. As a result, research on global warming due to the increase in the concentration of carbon dioxide in the atmosphere has become more active. One thing to note is a slight time difference between the age when the fossil of the atmosphere was created and when the snow fell for the ice containing trapped air. However, ice scientists have found that based on the result of several experiments, air bubbles are completely trapped in the ice when the density of the ice is 0.84 grams per cubic centimeter. So how long will it take for the bubbles to be trapped entirely? Snow glaciers estimate it would take 130 years at Camp Century, where only about 30 centimeters of snow cover per year. But at the base in Vostok, where the annual snowfall is only 5 centimeters, it took 3,000 years. In addition, there's an error in this value. Still, there's no doubt in the analysis results that the concentration of carbon dioxide in the atmosphere during the Ice Age was relatively low at 200 ppm. Since carbon dioxide is one of the greenhouse gases, the increase in carbon dioxide from the last ice age to the post-glacial or Holocene suggests that global warming occurred along with it. The ice age was dusty. It is not only snow or rain that falls from the sky. Various things such as substances floating in the atmosphere with multiple ions dissolved in rain or clouds come down. Therefore, by analyzing not the ice itself, but the impurities contained in it, it is possible to bring out an aspect of the past Earth environment that differs from the information obtained from isotopes. The representative impurity of ice is particle matter floating in the atmosphere called aerosol. Scientists' analysis of the ice revealed that the ice age was dusty. The graph on the screen shows GISP2 calcium concentrations in Greenland and dust concentrations in Vostok. The dark areas indicate glacial ages, suggesting that ice ages are more dusty than interglacial ones. As a result of chemical analysis, the aerosol contained in the ice cores of Greenland are mainly from East Asia, and the aerosols of Antarctica are mainly from the dry areas of Patagonia located in the southern tip of South America. There are 2 possible causes for the dust during the Ice Age. One is that the temperature difference between the equator and the poles has increased, and the wind has become more robust. The stronger the wind, the more dust is blown up from the land. And the extensive aridity of the mid-latitudes is another reason why the Ice Age was dusty. If atmospheric circulations had been strengthened, downdrafts would have been maintained in the subtropics, and arid climates would have been extended. In addition, it is possible that a lot of dust was raised from the continental shelf area that became land as the sea level fell and moved to Greenland or Antarctica. Since the 1990s, GRIP, GISP2, and North GRIP have been collected from the Greenland ice sheet, and in Antarctica, Vostok, which has gone through 4 ice ages, and Dom C and Dom F, which surpassed them, have been successfully recovered. This series of ice core studies have revealed most of the large-scale climate changes recorded in continental glaciers. Since then, scientists have been able to analyze seafloor sediments and glacial ice from more places to reconstruct planet Earth's 500 million-year-old climate. Analysis of the Greenland and Antarctic glaciers confirmed that ice ages were repeated in 10-year cycles. But why did it repeat every 100,000 years? The cause will be introduced in another episode. Please give a thumbs up, subscribe, and turn on notifications.